Presentation from the Mechanical Engineering Department from the University of Texas at El Paso. Here we have the spinning marble defense against hostile satellites. You can go ahead and meet Team 8, starting with Joshua Cervantes, Luis Loera, Gerardo Para, Jonathan Sotero, Alexis Gomez, and our professor, Dr. Khan. Here we have the project objective. The purpose of this project is to help increase the lifespan of new satellites. This fixed countermeasure should also be able to deter any hostile satellites or space debris without propellant, utilizing centrifugal forces. Here's the analysis of the problem. We also stated that in low Earth orbit, there's a lot of space debris, so that way that satellites could also have a deterrent or some kind of way to defend themselves. Here we also have angular velocity, centripetal forces, angular acceleration, and our counterweight centripetal equations, so that way we could counter those forces inside the system. We have the analyses of the problem. The key methodology that our project used was to consistently test the system and see how the new integration actually handled itself by designing it in Autodesk Fusion 360. Here's also a brief look at our components list so that way that you could see our 12-volt driver and the different kinds of software that we ended up using for this project. Here's also a brief look of our bill of materials where we can see every single component, all of it costing about $111.89. Here we have the functional flow chart where you have to load the projectile, then you turn on the system. Should be a delay for 5 seconds, then it'll increase speed all the way up to 300 RPM. Then it'll initiate the launch sequence. There is an emergency stop button, and there should also be a launch door that is initiated by the spring actuator towards the very bottom. Here we have the CAD and tabletop design with our first prototype. With the basic dimensions, we have the arm length right there, and our counterweight should also be 120 grams of our selected material. Final printed design. This is the final design with the launch door that could actually open with the spring actuator. Here we have the limitations and the future work. Due to the complexity of the project, time constraints, and other factors such as cost, the more simplistic approach was the best. System limitations that required us to dial back the RPM, such as a slip ring, and we also have gravity that affected our theoretical results. Future work, we would like to integrate this into a turret system, have heavier materials, and even include artificial intelligence so that we could detect things.
This was one of the earlier testings where we noticed instability within the arm, which led us to add a counterweight. In this next clip, we demonstrate the trigger mechanism as well as the increase in stability caused by the counterweight. With the addition of the counterweight, we are now able to hit 300 RPMs or stage 3 of the sequence. It was around this point we started to hit our first and major limitation of the design. Our means of release was an electromagnetic solenoid, but to get power to it, we had to add a slip ring. It was this slip ring that induced major wobble within the arm.
I have the panel here, the 3 LEDs. I can only test the solenoid and the LEDs. So if I press the start button, there's a delay before it starts, green, then yellow. This is second RPM, and then it reaches the last stage and activates the actuator, and then it turns off. And then if I do the same, now start, and then if I press stop, it just turns everything off.
To reduce the instability caused by the slip ring, we had to redesign the arm, which included a slot for the slip ring, which would take the load off of it entirely. We also had an addition of 2 new support gears, which held the arm in place. With 2 successful test runs, we wanted to implement the support rail, but as you can see, it is really unstable with it, and the launch door is not in effect.
The motor that spins the arm is connected to a driver, and we control the speed of the driver using pulse width modulation from the Arduino. And once we reach a certain speed, we have a solenoid magnet that is connected to a relay. So once we reach a certain RPM and the marble is ready to launch, the Arduino sends a signal to the relay and powers on the powers off the solenoid to let go of the marble. And we also have a start button and an emergency stop button. The motor won't turn on unless the start button is pressed, and at any point, if the emergency stop is pressed, the motor is turned off.
So for test 4 is a fully assembled prototype. Here we can see an updated arm as well as the control panel as well as the system mount all assembled. We included an actuator to control the launch door, which is triggered once we hit sequence 3, which is around 300 RPMs. The support railing reduces instability, so we have to redesign that.